in the last couple of lectures, we were deriving the equations for the laminar flow in a pipe, a pressure driven flow, where the flow is driven by a difference in pressure between the inlet of the pipe and the outlet. Okay. So, there is a higher pressure at the inlet and there is a lower pressure at the outlet, okay. And this drives the fluid flow from the inlet to the outlet. I had told you that pressure is the dynamical pressure that drives a flow is known only to within an additive constant, okay, within with respect to a reference pressure, whereas the thermodynamic or absolute pressure is always positive. The dynamical pressure that drives the flow for incompressible fluids is reference to a constant baseline, okay, and so it could be positive or negative. Okay. We had done a momentum balance across a differential volume, okay, and we had got an expression for the pressure variation across the rate of change of the momentum. Okay. It contained two terms. Okay. On the left side is the rate of change of momentum at a given location. Okay. On the right side is a viscous term plus a pressure gradient. Okay. While deriving this equation, one approximation that we had made was that the velocity Vx is independent of x. Okay. We had assumed that the velocity Vx is independent of the downstream distance. It varies only on the it depends only on the radial distance, the distance from the axis of the pipe. Okay. So, at the wall it has to be 0 and you would expect it to be a maximum at the center. Okay. So, that assumption I had showed you was valid provided the flow is incompressible by doing a mass conservation mass balance. Okay. If you take the change in mass is equal to mass in minus mass out at the locations x and x plus delta x, because the velocity is only in the x direction. The change in mass is related to the change in density within that differential volume. Mass in and mass out are related to the velocities at the surface at x and surface at x plus delta x. And we got the mass conservation condition here. Okay. And if the flow is incompressible, then the change in density is equal to 0. Okay. So, that means that Vx is independent of x. Second input, the pressure gradient, okay, is the pressure is only a function of x. Okay. The reason is because if I were to write an equation for the r momentum, okay, the momentum equation in the radial direction, then I would get the terms which are proportional to the velocity in the radial direction for the momentum in, r momentum in and r momentum out. Okay. The r momentum is actually 0 in this case, because the velocity in that direction is 0. So, all the momentum terms will be identically equal to 0, and therefore, you will just get the simple relation that the pressure variation in the radial direction is equal to 0. Okay. Pressure cannot vary on the radial direction r. Okay. For a steady flow, it depends only upon x. For a time varying flow, it can depend on both upon x and upon t. Okay. If the flow is a function of time, for example, if you were pumping the fluid with an oscillatory pressure variation, okay, where the pressure variation oscillates in time, then the pressure gradient at a location can be a function of time, but it will not be a function of r, because there is no radial velocity. Okay. Therefore, you will get back just partial p by partial r is equal to 0. Okay. So, if it is at steady state, then the partial p by partial x. Okay. So, I should add a caveat to what I said in the last lecture. Steady state, p is a function of x and partial p by partial x is equal to dp by dx. Okay. If it is unsteady, p can be a function of x and time. Okay. So, you will use the total derivative only at steady state. If it is unsteady, pressure could be a function of x and time. And the other thing that we did in the last lecture was to take the derivative of the entire momentum balance equation with respect to x. Okay. We took the derivative of the entire momentum balance equation with respect to x and used the condition that partial Vx by partial x is equal to 0 for an incompressible unidirectional flow. Okay. And that gave us the relation that d square p by dx square is equal to 0. Okay. If it is time varying, this would be partial square p by partial x square is equal to 0. Okay. That means that partial p by partial x is a linear function. Partial p by partial x is independent of x. Okay. That means that p has to be a linear function of x. Okay. P has to be a linear function of x. Okay. At the inlet it is higher, at the outlet it is lower, and it is a straight line between those two. So, pressure is a linear function of x, pressure gradient is a constant. This is true even if you have an unsteady flow. Okay. Even if the difference in pressure between the two ends is varying as a function of time. Okay. Let us say it is at one particular value at one particular time and it goes to some other value at some other time, the pressure at the two ends. The pressure in between is still a linear function, okay, between the inlet and the outlet pressure. So, the pressure at the inlet and the pressure at the outlet could vary with time, okay, but at each instant of time the pressure in between is a linear function, okay, a straight line connecting the pressure at the inlet and the pressure at the outlet. That is because partial square p by partial x square is equal to 0. Okay. That is because partial square p by partial x square is equal to 0, which means that partial p by partial x has to be a constant. It could depend on time, but it cannot depend upon x. Okay. Okay. So, let us now solve this equation, okay, at steady state. Okay. 0 is equal to mu by r plus dp by dx. Total derivative, because we are assuming there is no time variation, this is a steady problem. My apologies, there should be a negative sign here. Okay. And I told you that dp by dx is negative because pressure at the inlet is higher than the pressure at the outlet. So, dp by dx itself is negative. Okay. Okay. So, I get mu by r d by dr of r partial Vx by partial r is equal to dp p by dx. Okay. In this case, we know that Vx is not a function of x. Okay. Vx is not a function of x because it is incompressible, and I have assumed a steady flow as well. Therefore, Vx is only a function of r in this case. Pressure is only a function of the downstream coordinate, and the velocity is independent of downstream coordinate, it is only a function of r. Okay. And dp dx is a constant. Okay. So, I can solve this. Okay. d by dr of r dvx by dr is equal to r dvx by dr is equal to r square by 2 mu dx plus a, okay, integrate one time, okay, which means that dvx by dr is equal to r by 2 mu a by r. Integrate a second time and you will get Vx is equal to r square by 4 mu plus a ln of r plus B. Okay. So, this is the velocity profile. A and B are the constants of integration. Okay. So, these are determined from the boundary conditions. Okay. One boundary condition of course is that at r is equal to capital R, okay, or let me capital R is the radius of the pipe, and I am using a coordinate system. X is along the axis and R is perpendicular. Okay. And you would expect the velocity profile to look something like this. Okay. The velocity has to come to 0 at the walls of the pipe. Okay. At R is equal to R, Vx is equal to 0. Okay. At the center of the pipe, just by symmetry, okay, at the center of the pipe, just by symmetry, right, it has to reach a maximum, okay, at the center of the pipe, okay, which means that at r is equal to 0, dVx by dr is equal to 0. Okay. The slope has to be 0 at the center. Okay. Note that this is an axisymmetric configuration. The velocity does not depend upon the angle around the center. Okay. This is an axisymmetric configuration, and the velocity does not depend upon the angle around the center. Okay. So, therefore, you require that as you approach the center, the slope has to be the same in all directions. Okay. As you approach the center, the slope has to be the same in all directions, and that can be satisfied only if the slope is 0, okay, at the center, okay, or the velocity is either a maximum or a minimum. Okay. So, dVx by dr is equal to 0, okay, implies that A is equal to 0, because if A were non-zero, dVx by dr would go to infinity. Okay. Therefore, A has to be 0. Another way of understanding this is that the velocity is equal to A times logarithm of r. Okay. If the velocity has to be finite at the center, then A has to be 0, because the natural log of r goes to infinity at the center. Okay. So, therefore, A is equal to 0. The other condition gives you a relation for B. Okay. B is equal to minus r square by 4 mu dP by dx. Okay. Using these two constants, the velocity can be written as Vx is equal to minus 1 by 4 mu dP by dx into r square minus r square. Okay. R square minus r square, that is a parabolic velocity profile. Okay. The velocity profile is a parabola. Okay. Okay, it is called the Hagen profile, okay, for the flow in a pipe. Okay. It is a parabolic velocity profile. The velocity is 0, of course, at the walls where r is equal to capital R. Okay. The maximum velocity is at the center. Okay. Okay. V max is equal to Vx at r is equal to 0, is equal to minus 1 by 4 mu, sorry. Note that I had told you that for a pipe where the inlet pressure is higher than the outlet pressure, dP by dx has to be negative. Okay. So, when the inlet pressure is higher than the outlet pressure, dP by dx is negative, and therefore, the velocity is positive, okay, throughout the pipe. Okay. I can also express Vx in terms of this Vmax, okay, by dividing throughout by Vmax. I will get Vx is equal to into 1 minus r square r square, okay, when expressed in terms of this maximum velocity V max, okay, at the center of the pipe. Okay. At r is equal to 0, it is equal to V max, and at r is equal to capital R, it is equal to 0. The shear stress at the wall, okay, tau x r, force per unit area in the x direction acting at a surface whose outward unit normal is in the r direction, okay, is equal to mu times dVx by dr. Okay. If I were to express in terms of V max, okay, if I were to express this in terms of V max, I would get this equal to minus 2 mu V max, okay, into r by r square. Okay. So, this is the force acting at a surface whose outward unit normal is in the r direction. Okay. So, for a pipe, okay, if I have a cylindrical surface somewhere in between, okay, this is the force that is exerted at a surface whose outward unit normal is in the r direction. Okay. So, this is the force that is exerted on the cylindrical surface, okay, on the fluid that is within the cylinder. Okay. That force is in the minus x direction. Okay. The wall shear stress, tau x r is equal to, sorry, okay, should be minus 2 mu V max by r. Okay. So, the wall is exerting a force in the minus x direction on the fluid. Okay. The wall is exerting a force in the minus x direction on the fluid. The fluid is exerting a force in the plus x direction on the wall. Okay. So, the wall is exerting a force in the minus x direction on the fluid, and that force balances the force in the plus x direction due to the pressure difference. Okay. You recall when we initially examined the pressure difference in a pipe, I had told you that the force on the cylindrical surface area due to the shear stress, tau w into the force on the cylindrical surface area, that is pi dl, okay, is going to be equal to the difference in pressure times pi d square by 4, which is the cross sectional area. Okay. So, if you balance the backward force exerted by the wall on the fluid, okay, the wall is tending to retard the fluid and reduces the velocity to 0 at the wall. So, if you take the backward force exerted by the wall on the fluid, that has to be equal to the force due to the difference in pressure. Okay. Okay. Okay, that has to be equal to the force due to the difference in pressure between the inlet and the outlet. The force due to difference in pressure is delta p into pi d square by 4. Wall shear stress tau w into the cylindrical surface area pi d into L. Okay. So, based upon this I get, okay, tau w is equal to, okay, delta p by L, okay, into d by 4. Okay, the pi's will cancel out and I will get delta p by L into d by 4. Okay. If you examine this expression for the pressure difference, and I express this in terms of the V max in terms of the pressure. Okay. So, I will get minus 2 mu by r into minus r square by 4 mu, okay, dP by dx. Okay. So, this expression you can easily verify will be equal to okay, the mu's will cancel out, the viscosity will cancel out, and I will get this is equal to r by 2 dP by dx. Okay. Okay. Now, radius is equal to diameter by 2. So, these two are exactly the same, okay, except that one is expressed in terms of the difference in pressure across the ends, the other is expressed in terms of the local pressure gradient. Okay. And we already know that the difference in pressure across the ends divided by L is actually the local pressure gradient. Okay. So, this wall shear stress expression is just a momentum balance across the ends with a linear pressure gradient in between. Okay. dP by dx is a constant. Okay. So, we get back the same expression as we got for the wall shear stress by an integral balance over the entire pipe, okay, from this local, okay, description of the velocity field as a function of radius. Okay. So, we get back the same force balance in this case as well. The only additional insight we have here is that delta P by L is equal to dP by dx, that the slope of the pressure profile is actually linear. So, we have got the wall shear stress, okay. We have got the wall shear stress here. Now, we have to calculate the correlation for the friction factor. The friction factor correlation, recall, contains the average velocity, not the maximum velocity. Okay. Recall that the friction factor correlation contains the average velocity, that is the average cross sectional average velocity. Okay. And the average velocity is the flow rate divided by the cross sectional area. So, first we will calculate the flow rate. Okay. Okay. V dot is equal to integral 0 to r, okay, of so, for a pipe flow, okay, the velocity is varying as a function of position, okay, in the radial direction, where this is the radial direction r. Okay. How do we get the flow rate? I have to take the total velocity, okay, the total mass flow rate in a differential volume of thickness delta r and integrate it. Okay. What is the flow rate in a volume of thickness delta r? Okay. Flow rate is equal to the velocity times the area. Okay. Velocity, this is the volumetric flow rate. Okay. The velocity is mass per unit, length per unit time into area is length square. If you multiply Vx by the area, you will get the flow rate across a cross section. Okay. So, across this cross section of thickness delta r, the cross sectional area, okay, the cross sectional area for the cross section of a thickness delta r is going to be equal to the perimeter into delta r. Okay. It is going to be the perimeter into delta r. Okay. So, therefore, the flow rate, which is Vx times the perpendicular area, is equal to Vx into the perimeter 2 pi r into delta r. Okay. So, if I do it in terms of differentials, I will get Vx into 2 pi r dr is the flow rate. Okay. So, this is going to be equal to you have r power r square by 2 minus r square by 4. Okay. So, this is going to be r square by 4, okay, 2 pi V max into r square by 4, okay, is equal to pi V max r square by 2. This is the volumetric flow rate, okay, and the average velocity is equal to the volumetric flow rate by the cross sectional area of the entire pipe, okay, the volumetric flow rate divided by the cross sectional area of the entire pipe, okay. So, this is going to be equal to V max by 2. So, the average velocity is equal to 1/2 of the maximum velocity, okay, or the maximum velocity is equal to 2 times the average velocity. Okay. Therefore, the velocity profile can equivalently be written as Vx is equal to 2 V average into 1 minus r square by r square, okay, and the shear stress tau x r is equal to mu dVx by dr, okay, is equal to mu the wall shear stress tau w is equal to tau x r at r is equal to capital R is equal to minus 4 mu V a v by r. Okay, so, that is the wall shear stress. And we know that the friction factor, okay, the expression for the friction factor is I have to take the modulus of the wall shear stress because the shear stress is in the negative x direction. Okay. The stress exerted by the fluid on the pipe is in the positive direction, by the pipe on the fluid is in the negative x direction. Okay. So, this is equal to 4 mu V a v by r into 2 by rho V average square. Okay. Okay. I can write the radius in terms of the diameter because the characteristic length that is used for a pipe flow is the diameter, not the radius. Okay. So, this will be equal to 16 mu by rho V average d, where d is equal to equals to r, okay, or r is equal to d by 2. Okay. And this thing in here is the definition of the friction factor of the Reynolds of 1 over the Reynolds number. Recall that for a pipe flow, rho V average d by mu is the Reynolds number. Okay. So, this is 1 over the Reynolds number. Okay. So, I get F is equal to 16 by Re. Okay. This is the friction factor correlation for the laminar flow in a pipe, okay, which I derived for you by doing a balance over momentum balance over the pipe and then taking the wall shear stress, finding the entire velocity profile and then finding what is the wall shear stress and then using that in order to find out what is the friction factor correlation. Okay. So, this is the friction factor correlation for the flow in a pipe derived from fundamentals from the microscopic momentum balance equation. Okay. We will look at a couple of examples of how to use this starting in the next lecture. Okay. Okay, so, I will continue this then.